In this lesson, we're going to draw up probability distribution tables. A little bit of terminology to start with. We've got this idea of a random variable whose values can't be predicted but can be determined by experiment. So maybe like the number of heads we'll get if we throw 10 coins up in the air. The variable is represented by a capital letter and the value represented by a lowercase letter. That'll make more sense when we see one of these tables. And there's a few facts here that we'll be able to play with as well. Alright, we'll do the example and then refer to some of those rules. Part 1. Draw up a discrete probability distribution for a table of 4 children where boys are desired. I'm going to let x, the random variable, be the number of boys. I'm going to draw up now a tree diagram to evaluate what's the probability of getting no boys in a family of 4, 1 boy, 2 boys, and 3 boys. So just like in the previous lesson, we're going to have the first child can be a boy or a girl. Remember, since the outcomes of these are equally likely, I don't need to write the probabilities on the trees, on the branches rather. And then I'll look at the second child, which can be a boy or a girl. And then I'll do that again for the third and fourth children. So I've completed my tree diagram. I can then write my sample space. I'm going to list the outcome of my random variable here. So I'm going to essentially count the number of boys in each of these outcomes in my sample space. So in this first one, there's 4. 3 boys there, 3 boys, 2 boys, 3 boys, etc. as we go down. So the idea of a probability distribution table is that I'm going to write the possible outcomes of my random variable capital X with a lowercase x. So it can be 0, 1, 2, 3, or 4 boys. I'm going to look at what's the probability of my number of boys being equal to 0, 1, 2, 3, or 4. That's all this table is about. So all these outcomes are equally likely. I can just count the number of times 0 occurs divided by the number of outcomes in total. We can see 0 occurs just the once, so the probability would be 1 in 16. Look at how many times 1 occurs. I see it 1, 2, 3, 4 times. So that'll be 4 out of 16. But I'll simplify that to 1 on 4. So just remember, when I had p equals x equals 1, it was really 4 on 16, but I wrote it as 1 on 4. Do the same thing with 2, 3, and 4. Constructed is called a probability distribution table. It shows how the probability is distributed among the possible values of the random variable. So now I can probably go up to these things and explain what all this terminology means. This first one really means that the probability of each event, or each outcome, is between 0 and 1. Okay, which we expect, and we know that the sum of all these probabilities is 1, which means down here in this table, if I need to add all these together, I need to get 1. There's no other outcomes there. Alright, part B. Using the table, calculate the probability of getting 3 boys given that you already have 1. The way I'll do this is I'll write down that question in terminology. So the probability of getting 3 boys, so probability that the random variable is 3, given that I already have 1. Okay, given that I know it's at least 1. This big line means given that. So there's a big nasty formula here, essentially meaning we need to divide by something, but we can look at how it looks in reality. If I'm saying what's the probability of getting 3 given that I know it's at least 1, I'm only really considering those 4 outcomes, which means I'll take my probability of getting 3 boys and I'll divide it by all the possible outcomes. So I don't need to consider this 116 at the end. All I'll need to do is add together those 4 highlighted probabilities. I'll end up with something like a quarter divided by 15 on 16, and I can simplify those fractions to 4 on 15. Okay, probability of getting 3, given that I already have at least 1, 4 on 15, which is bigger than 1 on 4, which is what we expect, because it should be more likely that we'll get 3 if we already know that we have 1 boy. To reinforce this concept, we'll look at an example where the probabilities of each outcome aren't equal. 3 balls are selected from a bag containing 6 blue and 4 yellow. We're replacing it each time as well. Draw up a probability distribution table for the number of blue balls selected. So I'm going to let my random variable be the number of blue balls. It's important you do that so that when you look at the table, you know what that capital X is referring to. From here, I'll draw up my tree diagram with blue and yellow balls at each time, and I'll put the probabilities on the diagram as well. I'm only selecting 3 balls, which is good. So my table's not going to be too big. Okay, unlike the example we did with the cards, it's with replacement, which means that I take the blue ball, I put it back in, so there's still 10 balls, and there's still 6 blue balls in there. Go ahead and complete the rest of the table and the sample space. And again, I'm going to count how many blue balls are in each of these outcomes in the sample space. So 3, 2, 2, 1, 2, 1, 1, 0. I'm going to be making a probability distribution table of the number of blue balls that could possibly have occurred. So I know that it ranges from 0 to 3. However, since each time we split on the tree diagram, the probabilities aren't equal, it means that I won't just be able to count this one outcome out of 8. I'm going to need to find, for example, what's the probability of getting 3 yellow balls by multiplying all these probabilities that I see as I travel through the branches of my tree diagram. So I'd have to multiply all of these together to get, for example, 64 on 1000. Then I'll have to do the same thing for all of these 3 for 1 and add them together. So that I've found the probability of those cases where we get 1 blue ball, I'll add these 3 together and get 288 on 1000. And then I'll go ahead and do that same thing for the 2s and finally for the 3. After all that hard work, what I have is part A complete, which is drawing up my probability distribution table. So I can answer part B, find the probability of getting 3 blue balls given that you already have 1 blue ball. Again, I'll write this in terminology. What's the probability of getting 3 balls given that I already have 1? Which means I'm only looking at these 3 scenarios. I'll grab my probability of getting 3 blue balls and divide it by the ones that I'm considering. I don't need to consider the case where capital X equals 0. The variable equals 0. I'll end up with 3 on 13 as that probability. So from here, have a go at those problems in the text to practice this idea of constructing the probability distribution table.